let's talk about the concept of pH, which refers to power of hydrogen ion concentration. Okay, so that's what the pH scale means. And pH is a logarithmic function in which every increment is a tenfold increase or decrease depending on which way you are moving up or down the pH scale. So for instance, a pH of 1 is 10 times more acidic than a pH of 2, but it is 100 times more acidic than a pH of 3. Okay. We also have something known as the POH scale, which is the power of the hydroxide ion concentration. So very similar to the pH scale, except we are really focusing on the hydroxide ion concentration. So instead of using the autoionization constant of water to determine various concentrations in solution, we can use these formulas to help us get certain information as well. So let's take a look at this particular question where they're asking you to calculate the pH, the POH, the hydronium, and the hydroxide ion concentration of a 0.25 mole per liter hydrobromic acid solution. What I do is I always start off with a dissociation equation. This is a strong acid. When it dissociates in water, hence the aqueous, we get 1 hydronium ion, or I wrote it as hydrogen ion. Again, we know now it's probably more appropriate to write it as hydronium ion plus the bromide ion, okay, the anion. Again, where did that oxygen come from? Because you have to have oxygen on the left. Remember that the AQ stands for the water. So that's where that came from. So if we have a 0.25 mole per liter solution of HBr, then that means this concentration will also be the same because it is a 1-to-1, and same with the bromine ion. So what we know is this one is done. We have figured out that concentration. There are a number of different ways that you can go about solving for the remainder of these. There's different steps that you can follow. It really doesn't matter. I'll just show you what way I'm going to follow next. So for me, I'm going to calculate the pH. So if I am given the hydronium ion concentration, I can very easily calculate pH now. So pH is equal to the negative log of the hydronium ion concentration. So what I do on my calculator, I'm going to put in 0.25. I'm going to push my log button, and I put negative because that negative will take that negative away, and I end up with a pH of 0.60. Then what I can do is I can take a look at this relationship of pH and POH, and I can figure out what the POH is of this solution. So what we know is pH plus POH is equal to 14, which is the scale at which the pH scale and POH scale go to. So what we want to do is POH would then be equal to 14 minus the pH. So we have 14 minus 0.60, which gives us a pH of 13 decimal, or POH, sorry, of 13.4. So we have got that one done. Now what we want to do is we want to figure out the hydroxide ion concentration. So if I am solving for hydroxide ion concentration, there's really a couple of ways that you can go about this. You can use the relationship of OH concentration is equal to the anti-log, which is 10 to the power of the negative POH. So what we can do is we can plug that in on our calculator, and we can take 10 to the negative 13.4. Okay, so on my calculator, I have second function log button, takes me to that 10 to the x key, 13.4, and I'm going to make sure that that's a negative second function log, and I get 3.98 times 10 to the negative 14. So on my calculator, the space here means that that is an exponent. So 3.98 times 10 to the negative 14, and that's a concentration, so that would be moles per liter. The other way that I could have gone about solving for the hydroxide ion concentration would be to use that autoionization constant relationship. So we know that the autoionization constant for water is 1.0 times 10 to the negative 14. And we know that this is equal to the hydronium ion concentration multiplied by the hydroxide ion concentration. What I would do is I would then take 1.0 times 10 to the negative 14. I could divide it by 0.25, and that would give me my hydroxide ion concentration, which should be that. So let's take a look and see how that would work on my calculator. 1.0 times 10 to the 14 negative, and I'm going to divide that by 0.25. And sure enough, I get 4 times 10 to the negative 14. So if I do 4 times 10 to the negative 14, and if I was to put this to 1 sig fig, okay, or 2 sig fig, this ends up being the same value, okay? So there's two different ways that you can go about solving for different concentrations, using this relationship that we've learned previously or using the anti-log scenarios. Let's take a look at another question on your sheet. It asks you to calculate the hydrogen ion concentration, and you have a 0.25 mole per liter solution of barium hydroxide, which is a very strong base. What is the pH of the above solution? So barium hydroxide has the formula Ba bracket OH bracket 2, because on the periodic table, the valence of barium is +2, hydroxide is a -1. When you crisscross, you want to make sure that you have the brackets there. And when this base dissociates, because it's strong, it will produce the barium ion, and it'll also produce the hydroxide ion. Okay, and again, we really put the AQ there to say dissolved in water. We want to take a look at the relationship. For every one of these that dissociates, 1 barium ion is liberated and 2 hydroxide. So I put a 2 there. They're telling me that the concentration for this base is 0.25 moles per liter. So that means that the concentration of barium is also going to be 0.25, but the concentration of hydroxide is going to be 2 times that amount. So we're going to have 0.5 moles per liter. We want to know what is the hydrogen ion concentration in solution and what is the pH. We cannot go right to pH when we are given hydroxide. What we have to do is we have to figure out the POH first. So going back up here to our relationships, we know that if we're going to calculate POH, we need to take the negative log of the hydroxide ion concentration. So we're going to take the negative log of 0.5, and let's see what we get. So I'm going to put down 0.5 log, put the negative, and we get 0.30 as our pH, or our POH. We know this relationship, pH plus POH is equal to 14. So what we're going to do is we're going to figure out the pH by taking 14 minus 0.3, which gives us 13.7. So now we have the pH, and we also have the POH. We have the concentration of hydroxide. We just need to know what is the concentration of hydronium ions. Now again, we can use two different ways to go about getting that. We can take the anti-log, so here it is here. We can do 10 to the negative pH now that we have that value. So 10 to the negative 13.7. And we already know previously from grade 10 and grade 11 that on a pH scale, a pH that is greater than 7 is quite basic. So hence, this makes sense, being a base, that the pH would be kind of high. So what is the concentration of this in solution? We know that there is some of that in solution. Okay, so we need to take 13.7, take the negative of that, second function 10 to the x key, and I get 1.99 times 10 to the negative 14. So maybe I'll just take that to 2 sig fig, which is 2.0 times 10 to the negative 14 moles per liter. Now, you can also use the autoionization constant of water, just as we did before. So we know that this relationship exists. Knowing that the OH was 0.5, so if I was to divide this by 0.5, I should be getting this value. So let's just cross-check. And divide that by 0.5. And sure enough, we get the same answer. Okay, and again, your calculator might already put it into scientific notation, but this one is a little bit odd in that the space just represents that. So a couple different ways you can go about getting the hydrogen ion or hydronium ion concentration in this case. Hopefully that all makes sense, and best of luck to you moving forward with these type of calculations.